Okay. In this video, we'll talk about solving a system of differential equations with constant coefficients when you have complex eigenvalues. So again, we're looking at x prime equals ax, and we're solving for x, okay? And suppose that we have eigenvalues that are complex. The eigenvalues are the roots of the characteristic polynomial. And if A is a matrix with real entries, which it is for the purposes of this video and all the videos that I'm talking about, A is a matrix with real numbers. If the characteristic polynomial has a complex root, then its complex conjugate must also be a root. Okay, that's a fact about polynomials with real coefficients. The characteristic polynomial, if A is a matrix with real entries, its characteristic polynomial has real coefficients. So by a general fact about polynomials, if a complex number is a root, then the complex conjugate is also a root. So suppose there is a pair of complex conjugate eigenvalues. Say R1, which is lambda plus I mu, and R2, which is lambda minus I mu. So it turns out that the corresponding eigenvector, so you find an eigenvector for R1. Okay, maybe I'll just write it like this. It turns out that if V1 is an eigenvector corresponding to eigenvalue R1, then V2, let's say you take V1 and then you take the conjugate. So you just take the complex conjugate of the components of V1. So this is with the bar, right? It means complex conjugate. Then this is an eigenvector with eigenvalue R2. Which, if you think about it, isn't very surprising because R2 is just the complex conjugate of R1. Okay, so this is just a general fact that if you have A times V is R1V, then A times V bar, so the complex conjugate, is just going to be R1 bar V bar. That's what that's saying. Okay, so once you have your V1, you can find your V2, right? So you just take V2 bar, you take V2 to just be V1 bar, okay? So that gives you your V1 and your V2, and then you have the general complex solution. So you take all complex solutions to x prime equals ax, and if you take real and imaginary parts, there's a theorem that the real and imaginary parts of a complex solution are also solutions. That basically boils down to the linearity of the differential equation. So a reference for these facts, reference for this section would be Boyson de Prima, section 7.6. It's the section on complex eigenvalues. So if you have a complex solution to the differential equation, you can take real and imaginary parts and get solutions. So taking real and imaginary parts of, so your first solution, x1 of t, which is v1 e to the r1t, okay, if you take real and imaginary parts of this will give two linearly independent solutions. U of t and v of t. And these are going to be real valued functions that are solutions to your differential equation. So once you have your u of t and v of t, you know they're linearly independent, then that's going to give your answer. So the general solution this is talking about the real valued functions that satisfy the differential equation is x of t equals c1 u of t plus c2 v of t, where c1 and c2 range over all real numbers. Well, okay, maybe I shouldn't have a, let's see, this last part is if A is a 2 by 2 matrix. A 2 by 2 matrix with real entries. Then the general solution is C1 U of t plus C2 V of t, because when you have a 2 by 2 matrix, you're going to have two independent solutions that span the solution space. So here's an example. Let's say you wanted to solve x prime equals negative 0.5, 1, negative 1, negative 0.5, x. This is an example in Boyson de Prima. So first we need to find the characteristic polynomial. So let's call this matrix A. Characteristic polynomial of A. So for a 2 by 2 matrix, remember that we have a simple formula. It's lambda squared minus the trace, so minus the sum of diagonals. That's negative 1, so it's plus lambda, and then minus the determinant. Plus the determinant. Plus the determinant. So you're going to get 1/4 minus negative 1, so that's 1/4 plus 1 is 5/4. So you set this equal to 0, right? Lambda squared plus lambda plus 5/4 equals 0, and then you use the quadratic formula. So let's see, by the quadratic formula, lambda is negative b, so that's negative 1, plus or minus the square root of b squared, so that's 1 minus 4 times a, that's 1 times c, which is 5/4 over 2a, which is 2. So this is going to give you negative 1 plus or minus the square root of 1 minus 5 is negative 4 all over 2, and that's going to simplify to negative 1 plus or minus 2i over 2. So that's going to be negative 1/2 plus or minus I, right? You just divide the each part of the numerator by 2. So those are your eigenvalues. So we get R1 is negative 1/2 plus I. Now, of course, your R1 could be negative 1/2 minus I. It doesn't actually matter. So we just need to find one complex. So these are the complex eigenvalues, but the question is asking for the real valued functions that are solutions. So we just need one complex eigenvector. And so we just need to worry about one eigenvalue. So we just need to work with R1 and not R1 and R2. Okay. So we have R1, and then you find the complex eigenvalue by doing the same thing as you would with any eigenvector. You just do A minus R1I. So, but now you're going to get complex entries. So negative I, 1, negative 1, negative I. So that's just, you take your matrix A, right? And then you subtract R1 on the diagonal. And if you do that, this is the matrix you get. Now notice that this matrix is not invertible over the complex numbers, just like you would expect for a matrix that you get from looking at the eigenvalues. Because if you take the first column and multiply by I, you're going to get the second column. So these are not linearly independent columns as we would want for this matrix. So now we need to find an eigenvector, and it's easy for a 2 by 2 matrix. You just do the same thing as normal. You just flip. So you take this row and then you flip the entries. So the first one's going to be 1, and then the second one is going to be -I. But then you make one of them negative. So you multiply one of them by -1. So let's just multiply the second one by -1. So you get 1i. And you can check that if you take this matrix and multiply it by 1i, you get 0, 0. So v1 is an eigenvector of A. Okay, so now we write x1 of t. This is one of our complex solutions. It's just v1, so 1i, and then e to the rt. So r1 is -1/2 plus I, and then this times t. Okay, so this is one of our complex solutions. The next step is to find the real and imaginary parts of this. How do you find the real and imaginary parts of this? So first, I'm going to write this out. So this is 1i times e to the -1/2 t times e to the it. Okay, so in general, if you have e to the a plus bi t, that's just going to be e to the at times e to the I bt. And then that's e to the at times parentheses cosine bt plus I sine bt. Okay, so that's what I'm doing here. So I'm going to write this as 1i e to the -1/2 t times cosine t plus I sine t, right? Okay, so now what I want to do is I want to actually write this whole thing out as something plus I times something. And what's that going to be? Well, I distribute this e to the minus it across, okay, and then I have that on the top and bottom. So the first component is I'm going to have e to the -1/2 t times cosine t. And then I still have this plus I times e to the -1/2 t sine t, right? So that's the top, and then on the bottom, I have this I here. So on the bottom, my real part is actually going to be, so what's going to happen is this I here is going to be multiplied by this I here, and then you're going to get -1. Right? So I have this -1, and then I have this e to the minus it, which is being multiplied by sine t. So I end up getting -1 e to the -1/2 t times sine t. And then for the imaginary part, so on the bottom, I have I, right? I have this I, and then I have this e to the -1/2 t times cosine t. So this I is the I that shows up here. So then what goes in the blank is e to the -1/2 t cosine t. Okay. So that tells me, so now I've split up the x1 of t into this real part. This is the real part of x1 of t. And then this part, that's the imaginary part. Now the I is not part of the imaginary part. So the imaginary part of x1 of t is this function in the vector. So that gives me my answer. So my general solution, finding all the real valued functions that satisfy the differential equation, is x of t equals c1 times e to the, I'll write it as minus t over 2 cosine t minus e to the minus t over 2 sine t plus c2 e to the minus t over 2 sine t e to the minus t over 2 cosine t, where c1 and c2 are real numbers. Okay? And if you want to make this look a bit nicer, you could factor out the e to the minus t over 2 from each of the vectors. That's another way of writing it. Okay, so you could write it as c1 e to the minus t over 2, and then times cosine t sine t plus c2 e to the minus t over 2 sine t cosine t. That's also correct.